Oh, well, any case, okay. It's good to be here. Hello, everyone. As Karel said, my name is Per Larsson. I work as an assistant professor at the Department of Pharmacy at Uppsala University in Sweden. And so why am I here at this workshop? It's Karel's fault. He came to our department and worked for a few months as a research scientist while your wife was doing a postdoc, right? Yeah. So that's why we got to know each other, and then he invited me to come and give this talk for this workshop. So it's really nice to be here. Karel also gave me this title, In Silico Drug Delivery Optimization. So I wasn't exactly sure what to fill this talk with. So what I'm going to do is I'm going to give you some examples of how we and others have used in silico tools to work with more towards the usage of. So once you have designed your compounds and you have a reasonable idea that this compound will probably work as a drug, or at least as a drug candidate, what do you then need to do with it in able to be able to put it out on the market? So just as a starting point, some of the challenges that are becoming increasingly more important for pharmaceutical companies, we have this decrease in research and development efficiency. That's essentially saying that it's becoming progressively more difficult to take a novel drug candidate to the market. It takes longer and longer time, and it costs more and more money. And in fact, some people say that these days the largest chunk of where big pharma spends their money is on failed projects, essentially, and projects that fail for various reasons, obviously. But as you will see, or as I will try to show you, in many cases, those failures perhaps could have been avoided if one had put better use of in silico tools to try to understand certain aspects of why those drug molecules in the end didn't deliver as we think they did. And there is also this concept of switching essentially from blockbuster drugs into niche, or what is called niche buster drugs. So blockbuster drugs are those drugs that generate sales typically in the excess of $1 billion, let's say per year. So they are, from a pharmaceutical point of view, they are nice to develop because you get a lot of return on investment, so to speak. But that market, or that number of drugs, seems to be also to be declining. And so big pharma is progressively more targeting niche buster drugs, where they can develop drugs for smaller parts of the population to essentially to meet the unmet medical needs of smaller patient groups, where they can develop drugs that are more targeted towards particular populations or particular drugs. And I think you might have seen this slide before. I looked at some of the workshop material, and I saw that this was already in Karel's introductory presentation. But again, then just to illustrate the point, so this shows us so for each decade from the 1950s up until the turn of the century, so the number of drugs that have come out per $1 billion spent continues to decrease, even though we make a lot of new improvements in terms of manufacturing technology, drug discovery, and so on. But there is this reducing towards fewer and fewer drugs actually reaching the market. And to circumvent that, or one of the problems has to be solubility or poor solubility of these drug compounds. So if you look on drugs from a patient-centric point of view, for most patients and for most diseases, one should say, the preference is generally to take your medication as an oral dosage form, essentially as a tablet that you can swallow. That is the most the easiest way for you as a patient to take your medicine. But then that leads us into this problem of poor solubility of many of the novel drug candidates that are out there. So I put a figure here of 75% That might be a little less or a little bit more than that, but it's around that number. And you also have this effect that comes into play when we talk about oral administration of drugs, the so-called food effect. So for about 30% of all of the medicines licensed since 2010, you get different outcomes from a patient point of view if you're taking a meal or not before you take your medication. So clearly, and that is not acceptable from the point of view of doctors. It's not acceptable from the point of view of patients either. So we need to understand how all of the effects in terms of to be able to better predict essentially the of the drugs. So there is a need also for a patient-centric dosage forms. I think this is sort of what I said before as well about the niche busters. And Big Pharma is also interested in getting to the market as early as possible to have a first move advantage into the markets. So I will focus now on solubility essentially, because that's the main problem behind why a lot of promising drug candidates in the end fail to reach the market. It's because of poor solubility. And the reason why many of these, or one of the reasons why many of these drug candidates display poor solubility is that when you in libraries or however you design your, and we heard from the previous talk, different ways in which you can design novel drug candidates. Those assays largely tend to focus on selecting compounds with a high affinity or high selectivity towards whatever that is that you're binding to. And not so much focus is being put on solubility. So solubility sometimes sort of gets left on the wayside. Which means that, again, newer drugs are becoming more and more insoluble. And if you think about it from the point of view of an oral dosage form, it's really the soluble form of the drug that can pass through the intestine and into systemic circulation. So you really need the drug to be dissolved in order for it to be able to exert its effect. And just breaking that down again, so this is somewhat of an old slide, but it sort of still gets the point across. So for the top 200 oral drugs currently on the market, we see that about 40% of them are coined as practically insoluble, which means that they are essentially useless as they stand from the point of view of administering them in an oral dosage form. So something needs to be done about that. You need to add components to formulate the drugs in such a way that they become soluble. And only sort of about 25% of the drugs display a high enough solubility to be able to function without any significant investment of time and energy into the formulation. And again, one can also think about, so different drug molecules, these are sort of some of the drug molecules of more modern type that come out of these drug discovery projects or assays that show this problem of poor solubility. So we have drugs that are weak acids or bases that are not ionized. Different kinds of hormones often contain these halogenated or often contain halogenated elements. We have different kinds of lipophilic molecules, amphiphilic molecules, and also I'm sure there's the same thing here in the Czech Republic. There's currently this hype about biological drugs. So instead of using small molecules as drugs, you use peptides and protein as drugs. And those are also, from the point of view of solubility, they have other problems, but from the point of view of solubility, they are also very problematic. And one way of sort of trying to understand how solubility comes into effect is to use this so-called biopharmaceutical classification system, which was put forward by Colin Powton in about 2006. So one can divide, dependent on how soluble and also how permeable across a biological barrier your particular drug compound is, one can divide drug molecules into a certain number of classes 1, 2, 3, and 4. So where you want to go, or where you want your drug to be, is to be up here as a class 1 drug that shows both high solubility, so that it dissolves rapidly in the human intestine, but also that it has a high permeability. But as I've tried to illustrate, that's more often than not the case, that we are not here. So typically we are either in any of these other classes. And so from the point of view of optimizing your particular drug, if we are in either of these two categories where we have low permeability as the common factor, there's not so much that we can do in terms of formulation work to improve the performance of this drug. So then one has to do different kinds of lead optimization techniques to try to come up with other ways of improving essentially your drug so that it increases the permeability. But if you are here in the class 2 with low solubility and high permeability, then one can usually design the formulation. So the other molecules, the other co-solvents, the other excipients that you put in your final medicine to try to increase the solubility. And what I am going to talk about or present is a couple of examples of both we and others have used in silico methods, both sort of classical machine learning techniques, but also simulation methods primarily, to try to understand what happens when we put a particular drug molecule into a system when it is also surrounded by other components in the final formulation. Sorry. And then just as a final introductory slide, this is how we view the process of dissolution, essentially, of the thermodynamics of solubility. So you start from the crystalline form of your drug, and then that crystal needs to somehow break up, which is a process that costs free energy. And here we talk about so-called brick dust molecules, so essentially molecules that are very stable in their crystal lattice, like a brick. Then somehow we need to form a cavity in the solvent, where the molecule then subsequently inserts itself in a process that then gains free energy. And here we can have the other type of molecule called grease ball molecules, which are solvation limited in the sense that they have an unfavorable free energy of interacting with the surrounding solvents. So this is a picture from a review last year about using in silico tools to predict solubility. And so I think this is now my final introductory slide. Yes. So there are a number of ways that pharmaceutical scientists are working with drugs to try to improve in particular oral delivery of poorly soluble drugs. And as you can see, you can do different kinds of modifications. You can do chemical modifications, you can do physical modifications, and you can also, last but not least, change the route of administration. But again, as I said, we prefer our drugs to be administered orally, so this is not where we go in the first instance. So then one can think about different ways of chemically modifying our drug, making PA adjustments to maybe shift the ionization states of a molecule towards a charged state or towards a non-charged state, whichever is more favorable. One can design your drugs as a prodrug. This is essentially your drug with some chemical modifications on it that then get cleaved rapidly to deliver the final parent drug. Or we can make various physical modifications. We can do modifications to the solid state. We can decrease the size of the drug particles. We can add in a number of co-solvents. We can also add in surfactants and lipids. And also one can make complexes with cyclodextrin, which is sort of like a spherical sugar molecule that has a hydrophobic pocket inside. So there you can insert hydrophobic molecules and in such a way increase their solubility. So I will focus on for the remainder of the talk, work about understanding what the effects of modification of the solid state has on solubility, what happens when we put in co-solvents, and also similarly what happens to solubility when we have systems that contain the drug, but also different kinds of surfactants and lipid molecules. And feel free to interrupt me if anything is unclear at any point. As I said, I wasn't sure exactly what the target audience would be, so I'm trying to keep this on a general level and give you a broad overview instead of going into the nitty-gritty details of equations and so on, which I think you can read for yourself in the papers. Right. So my first example is work that we have done at Uppsala University, and that is involving using multivariate statistics and machine learning, I should say, to predict drug solubility in formulations. And as you will see, when I say machine learning here, it's not perhaps the more fancy stuff that both was presented this morning and also what Thomas talked about yesterday. So we have developed simple sort of partial least squares models and PCA plots, but they get you a fair way, I would say. So in this work, we had a bunch of compounds. This is a part of the table from that paper, and we measured a bunch of molecular descriptors, such as the molecular weight, the log P, which tells you the partition coefficient, so how hydrophobic or how hydrophilic is this particular compound. We have the melting temperature, we have the polar surface area, and also the number of double bonds and rotatable bonds. And so we had I think, or I shouldn't say we, the PhD student who did this had somewhere between 30 and 40 compounds in total that she characterized in this way. And then these are then simple PCA plots where we divided the data set into a test set and a training set. And we did then principal least squares regression to try to come up with models that essentially allows us to see how these molecular descriptors are able to predict or can be used in a machine learning context to predict solubility of drug molecules. So we did PLS, which I try to illustrate here. So PLS is a machine learning technique that it's a bit like PCA. The main difference is that we take into account also the variation in. So in PCA, you're interested in the variation in your observed or in your training set. In PLS, we also take into account the variation in your test set at the same time. So we try to maximize the covariance between these two, the test set and the training set. So essentially, it's two PCAs combined that gives you a final machine learning model. So we had a bunch of compounds, as I said, and then we developed a number of different PLS models shown here. And you have the reference if you're interested and want to go and look into details. So these are different machine learning models that try to predict the solubility, and the difference is in terms of which exactly molecular descriptors that went into the different machine learning models. So as you can see, and we predicted then the solubility for these drug compounds in soybean oil, so essentially a long chain lipid, and then we have this Captex, which is a trade name for a mixture of different medium chain lipids. And as you can see, from very simple machine learning methods, we were able to quite well predict or explain the solubility in these excipients. So these, I don't have any R squared values, but I think this one is about 0.8 or so, and this is similar. So this, I think, shows that you don't have to use necessarily any of those fancy. There's nothing wrong with those deep learning methods or anything. I mean, don't get me wrong. They work and they are really nice. But with quite simple machine learning techniques, one can go a long way. And then we went further, and we wanted to also to understand. So what happens now if we also put in solubility measurements in individual excipients into our machine learning methods? And so again, we did that, or Linda Alskär, who was a PhD student at the department, did that. And we did that for 4 types of so-called lipid-based formulations. So these are essentially systems that contain a mixture of different kinds of lipids and co-solvents with the idea to increase solubility. And we have here, so they differ essentially in the content in the number of lipids that they contain. And as you can see, we were able to come up with quite nice machine learning methods or machine learning techniques that allows us to predict the solubility of these compounds in these lipid-based formulations. So this is quite nice. Yep. Okay. So that was the end of my first example. I'm going through them relatively quickly, but this is just to give you an idea of how we use different kinds of in silico tools to understand what happens with drugs as we try to put them to the market. So my second example is about using not machine learning techniques as such, but rather molecular dynamics simulations to try to actually calculate the solubility of a particular drug in binary mixtures in this case. So this was work that was published in from the Mobley lab in 2015. And the basis for this work is the so-called chemical potential. So if you aren't familiar with the concept of a chemical potential, this is essentially a measure of the change in energy as one changes the number of particles in the system. And the important thing with respect to solubility is to realize that solubility is an equilibrium between the solid state and the liquid state of a particular drug molecule. And at that equilibrium, the chemical potential between the solid state and the liquid state are the same. And yeah, so this is the sort of the start for this work. And then after some algebra, which is again in this paper, I'm not boring you with the details. One can arrive at an expression that looks like this, that allows us to calculate so this is now the excess or the relative solubility. So it's important to realize that it's not the absolute solubility, but it's the solubility relative to that of an ideal solution. And the important thing here is that this expression essentially only contains the chemical potential. And the chemical potential, it turns out, is nothing other than the Gibbs free energy, which can be calculated from molecular dynamics simulations. So in this work, they did that for these 5 compounds and simulated them in binary mixtures of water and ethanol at different mole fractions. And you get something like this. So again, these are rather nice results. So here we have for 3 of the compounds, the predicted or the calculated solubility values versus the experimentally determined solubility values as dotted lines. And again, for the entire data set, the correlation, the R squared of this is 0.7 almost. So it's not perfect, but this is something that can be done. These are relatively small systems, even though there is a number of simulations that you have to perform at each point. Each such single simulation isn't particularly demanding. So in a reasonably short amount of time, one can get an idea for how the solubility is modulated as we increase or decrease the fractions of water and ethanol in this case. And so what we are now trying to do is to follow up on this work and see if it is possible to use this approach. And instead of having water and ethanol, we have water and, let's say, lipids, or water and something else that is more biologically. And they also did they also published another paper in 2016 where they also calculated, so what happens if we have, for a particular drug, is it more soluble in solvent A or in solvent B? And so this is why this is called relative solubility. And as you can see again, they were able to get quite decent correlations by performing, again, fairly simple molecular dynamics simulation methods. Yep. So my next example is about using simulations to understand stability and solubility in amorphous drug systems. So first of all, I have to say, what is an amorphous drug system? So drugs, or the solid state of, you can have many different solid types of solid states of matter, but in a crystalline state, you have a long-range order. So each drug molecule is arranged in a perfect crystal lattice. So you have long-range order in your system, whereas and the difference to an amorphous form is that long-range order no longer exists. So this is work that we published in Journal of Controlled Release 2 years ago now. So what this shows you is for two drugs, indapamide and glibenclamide. Not sure what they, I think, let's see. Yeah, this is an anti-hypertension drug. This is, I think, a diabetic medication. So these two drugs have very different solubility. And in this particular project, we were interested in what happens if we also add in a polymer to these systems. Because that is also a way of modifying the solid state of your system. So by adding in this polymer, one can take the drug essentially from a crystalline state to an amorphous state and thereby increasing its solubility. So we did that for, we had also two additional drugs, but I don't show the data for those two drugs here. So if you do that for indapamide and for glibenclamide, what these figures show you is over time and for various amounts of polymer, what is the solubility of these drugs. And as you can see, for indapamide, so the green line first is the intrinsic solubility. This is the solubility that you would have for this particular drug without any modifications, without any add-ons. So anything that you do to this drug to formulate it on the market, you should strive to increase the solubility over this green line. And similarly, this is the green line for glibenclamide. So this is the baseline solubility. So if we add in different amounts of polymer, we increase the solubility of this drug, which is good. That what we were supposed to happen. But then as time moves on, for glibenclamide, the solubility drops down again. So this is essentially an indication that although initially we were able to take this system from a crystalline state to an amorphous state, over time that system is reverted back more and more to its crystalline state. And if you were to follow this line out here, you would see that eventually it would coincide with the green line so that everything is going back to its crystalline state. Whereas for indapamide, the situation is not that. So for a particular amount of polymer, we are maintaining the system in a, so this is called a supersaturated state, where we have a solubility that is increasingly higher than the baseline solubility. And so we wanted to understand what is the difference, what does the polymer do differently to indapamide than to glibenclamide that allows it to maintain essentially solubility here at this supersaturated state. So this is, now we have increased the solubility about threefold or so over the intrinsic solubility by adding this polymer. So we did a bunch of simulations. So these are just of those two systems. We have the water molecules as this sort of transparent blue surface, and then we have the polymer as green. That's the green stuff. And here we have indapamide. It's a bit difficult to see since for some reason we chose to color the drug molecules blue as well, which was in hindsight a very bad choice. But you have these darker blue areas are the indapamide molecules, and over here again we have the polymer in green, and then we have the glibenclamide molecules in red. And so okay, so it's a bit difficult to see, and it's not something that you can see from these. Here is that we have a dynamic equilibrium in the sense that we have molecules, drug molecules, that move in and out of interacting with the polymer and with water. So we are simulating a dynamic system, which is good. And so then, then we, from the simulations, we did a very simple thing, and we calculated the number of hydrogen bonds that are being formed between the drug molecules themselves, and between the drug molecules and the polymer. And this is a really a poor histogram, but essentially you want to compare the bars that have arrows beneath them with the same color. So we did a bunch of different kinds of simulations where we varied the amount of drugs and the amount of polymer to be able to come up with systems that one can compare, because these two drugs have very different solubilities. But if you look at the middle bar, so this corresponds to a situation where we have the same number of drug molecules in both cases. So the same number of indapamide molecules versus glibenclamide molecules, which is nice because then you can compare directly the number of hydrogen bonds per molecule. These two other bars are other situations where we didn't do that. But then if you look at this, so here we have the number of hydrogen bonds between indapamide and the polymer per molecule. So it's about 0.8 on average. And the same then here. So these are the number of hydrogen bonds between glibenclamide and the polymer. And as you can see, it's only about 0.6 number of hydrogen bonds per molecule. So it's a significantly fewer number of hydrogen bonds between glibenclamide and the polymer versus indapamide and the polymer. And there is also fewer number of hydrogen bonds between individual indapamide molecules than there are between individual glibenclamide molecules. So what this tells us is that by adding this polymer into the system, we are able to prevent, in this case, the indapamide molecules from forming hydrogen bonds with one another, which is what they need to do to be able to form the crystal lattice that we don't want them to form, because that will lead us to a decrease in solubility. Whereas here, for glibenclamide, we see that we form, relatively speaking, fewer hydrogen bonds between the drug molecule and the polymer. So this, we think, then sort of explains on a molecular level those results for why adding in the polymer gave us a stabilization of the supersaturated state and a higher solubility for indapamide versus glibenclamide. Let's see, how am I doing on time? It's okay? Yeah. Right, and so my fourth example is using so-called Flory-Huggins theory, again together with molecular dynamics simulations. And so Flory-Huggins theory, I will explain that in a second. So this is a study, this is the oldest example that I have. This was published in 2008 from a research group in Canada, where they wanted to understand the solubility, or they wanted to calculate essentially the solubility of this compound, docetaxel, which is an anti-cancer drug. It's approved for treatments of I think, breast cancer, prostate cancer, and a number of other different kinds of cancers. And so they wanted to understand how one can formulate this drug in these different kinds of excipients. These are essentially lipids. They also had vitamin E in this data set for some strange reason. I wanted to understand if it is possible to use simulations instead of going and performing the actual solubility measurement. Can we predict solubility from simulations rather than doing it in the lab? And so this is a snapshot from their paper. So they use the compass force field and a software called Material Studio. So they have, compared to most other simulations, this is a relatively small simulation setup. They only have a few drug molecules, 1 or 2 or 3, and they have a bunch of, let's say, a couple of hundred lipid molecules. So a fairly small simulation system. They also have an incredibly advanced system or flow chart for setting this whole thing up. I'm not going to bore you with the details, but so essentially in the end what they do is to use so-called Flory-Huggins theory And Flory-Huggins theory it's a concept back about 100 years or so, and it was originally devised to come up with as a theoretical model to be able to predict why two polymer systems, if given two polymers, will these two polymers mix or not? And you do that by calculating this so-called Flory-Huggins interaction parameter. It's calculated through this expression. So you have the molar volume of your system, and then you have this Flory-Huggins energy, which measures the change in energy as you mix two compounds together. And from Flory-Huggins theory, you can combine, or you can compute, you can show that you can compute this energy of mixture from this expression using, again, another energy, so the cohesive energy density, which is a measure of how much the energy changes when you mix these two types of molecules together. And this relates to simulations or in silico tools in such a way that these two quantities, this is essentially the energy of each individual molecule in vacuum and the corresponding energy of that molecule when it sits in the mixture. And then you can also, and if you do that and you vary the mole fraction of your drug molecule and your excipients, you can compute this delta E mix, and you can plug that into this formula. Again, I'm not going into details. You can look up the maths. This is sort of published over and over again. And what you get is, so from Flory-Huggins theory, you can say that when the value of this parameter is below 0.0, one can then predict from Flory-Huggins theory that these two polymers or these two molecules will mix. So one can use then that with simulations. So if one varies the mole fraction in this case, so they vary the mole fraction of the cancer drug and with the other excipients, so different kinds of lipids. And then you plot, you go through this process of calculating the Flory-Huggins interaction parameter, and you plot the Flory-Huggins interaction parameter versus the volume fraction or the mole fraction of your drug. And when that line gets above 0.5, so essentially this point, one can reasonably take that as a measure of the solubility, the calculated solubility in this system. And so they did that, and I apologize for this slide. I stole it from the paper directly, so it's a bit hard to read. But so if one then makes this plot and goes in and reads off, so what is the volume fraction of dtx when the value of my Flory-Huggins parameter is at 0.5. So for these different excipients, they calculated, so these are the calculated solubility values. These are now, as opposed to my previous example where I showed solubilities, these are now actual solubility values. This is what you would go and measure also in the lab. And so as you can see, there is a rather nice correlation between the simulated, the values that are obtained from calculations versus what one actually measures in the lab. So this shows that at least for some systems, one can use actually 100-year-old theory to calculate solubility reasonably well instead of having and going and performing the actual experiment. And the important thing here is, of course, that it's much more easier and much more efficient to use the in silico method to calculate the solubility as opposed to performing the actual or measuring it in the lab. Right. And so my fifth and final example, which is work that we have been doing at Uppsala University. So this is an example that where I'm not going to talk about solubility anymore, but rather about drug partitioning. So what happens if you take some medication orally? That tablet goes into the stomach first, and then it eventually is released into the intestine, where it is absorbed into systemic circulation. And traditionally, one has always assumed sort of that if you take 10 different people, the amounts of lipids and so on, or amount of content in the intestine is largely the same between each individual. But there is a growing realization that that's not really the case. And also you have this, as I mentioned initially, the food effect. So dependent on whether you have eaten or not, you have different amounts of lipids and different amounts of bile salts in your intestine, and they all form different kinds of aggregates. So they form micelles, they form bicelles, they form vesicles, they form lipid droplets, and this is a very dynamic system, and it's also a system that affects the solubility of your drug to a large extent. And so what we have done here is to use again molecular dynamic simulations to try to see if we can understand something about how different amounts of lipids and bile salts affect drug partitioning. So not solubility, but partitioning. And we have in this system, or in this study, we had two molecules. So we had one lipid, which is this guy over here. And then we also had a bile salt molecule, which is this. It's called taurocolate. So it's essentially it's cholesterol. It's a sterile skeleton, but then it has this additional tail with this moiety that separates it, or that differentiates it from cholesterol. So we threw in a bunch of these molecules in a simulation software, and out essentially came this. So this shows us, or this shows a lipid bilayer consisting of the lipid, where we have also taurocolate molecules inserted in a very non-random fashion, it would seem. So they always seem to prefer to interact. You have some taurocolate molecules in the upper leaflet, you have other taurocolate molecules in the lower leaflet, and they always seem to prefer to interact in this fashion. So they formed transmembrane clusters consisting of 2 taurocolate molecules from the upper leaflet and 2 taurocolate molecules from the lower leaflet that were stabilized by these hydrogen bonds. And so what does that have, or why is that so? So what this shows you first, so we wanted to investigate, is this the most, why do we always see these taurocolate molecules clustering together as groups of 4? Why not 5 or 3 or 15? And so we did a bunch of free energy calculations, essentially varying the amount of taurocolate in the membrane. So here on the y-axis we have the potential of mean force, so this is the free energy, the stability of an individual taurocolate molecule. And initially, so we have a situation where we have this green line, which shows us the free energy of inserting a single taurocolate molecule into a lipid bilayer. So here the free energy is even positive in the center of the bilayer, which shows us that there is some sort of barrier towards inserting an initial taurocolate molecule. But once we have that, the free energy drastically drops and gets to about this point. But where we have 4 taurocolate molecules already inserted, energy doesn't seem to be decreasing any further. So we think that is sort of at least qualitative evidence for why we always see in our simulations these clusters with 4 taurocolate molecules. And then we also tried to vary the amount of taurocolate outside of the lipid bilayer to see if that has any effect. And this was an attempt to model using in silico tools the inter-individual variability in terms of bile salts. So here you want to compare the red line and the purple line, and as you can see, so this red line, that's the same as this red line here. So this is the free energy of clusters containing 3 or 4 taurocolate molecules, and this purple line is the shift in free energy if we also add in extra taurocolate molecules that are not interacting with these explicitly, at least. So there is a small shift in the minima, but the overall position stays the same. But then we are also in what consequences does this have for drugs? So can we use this to say something intelligent about what would happen if one takes a number of different drugs, given what we know about what the contents of your intestine are, essentially? So how can we in any way use this as a tool to try to personalize the dose that you would need for these drugs? So we tested it using these 3 drugs: carbamazepine, felodipine, and danazol, and in the presence of only lipids or lipids and bile salts. And as you can see, at least for danazol and to some extent for felodipine, which are the most hydrophobic drugs, the presence of taurocolates in the human intestine has quite a large influence on the partition-free energy of these drugs. It doesn't seem to affect that much carbamazepine, and we also did the green curve is ethanol. But at least for these hydrophobic compounds, there is a drastic change in the partition coefficients, so essentially how much drug goes into these colloidal structures that are being formed in the micelle. And if it goes in and it stays there and it can't come out again, that means that the dose that is available to you or that can be absorbed is greatly reduced. And that's a problem, of course. But yeah, and again, this shows you that one can use quite simple simulation methods to try to understand quite complex phenomena. And I'm getting towards the end of my presentation, so I've tried to show you that solubility is really important. So once you have your drug candidates or your lead compounds, your compound candidates, you also understand something about solubility to be able to take them to the market. And using different kinds of in silico tools can really help, at least for some systems, to predict solubility. And this is something that we and others, I should say, are currently working more and more on, because we think that using calculating solubilities in the computer essentially can save a lot of time and effort, instead of one having to go and try individually for each drug molecule what is the solubility in these excipients before then one can reach an intelligent decision about formulating a final product. Yeah, so that was that. Thank you for your attention. Are there any questions now or later? Yes.